thank you everybody for coming. My name is Alan Rubin at UCLA, and today I'll be talking about stony-iron meteorites. There we go. When we have primitive or undifferentiated meteorites, like this H-chondrite faucet here, the metal and the silicate grains are mixed together. In this particular image here, the metal grains are white in color, the silicate grains are the dark material over here, and we can see that the metal and the silicate are more or less homogeneously distributed. This is an undifferentiated meteorite, a chondrite. It's primitive, and this is the way the meteorites are in their initial pristine state. If we look at an asteroid, in the schematic diagram over here, again, if it's a chondritic, unmelted, undifferentiated asteroid, the metal grains, indicated here by these little white pentagons, are more or less homogeneously distributed in the body. If primitive chondrites are melted, two immiscible liquids will form. A metal liquid, which is much denser than the silicate liquid, so the metal liquid will sink to the gravitational center of the body and form a metallic core. The silicate liquid will rise toward the surface and eventually crystallize into a silicate mantle and a silicate crust. This is very similar to oil and water, as we see here at the bottom left. Oil and water are immiscible. They do not dissolve in one another. Oil is less dense than water, and so if we have a mixture like this that reaches equilibrium, the oil will float to the top of the liquid and form a scum at the top, and the water will be beneath. Meteorites that were melted in their parent bodies suffered separation of their metal and silicate. Metal sinks to the center, silicate floats to the center and to the top. And these rocks are said to be differentiated because there are different layers in such a body. These meteorites, the stony meteorites that are differentiated, are the achondrites, which means they do not contain chondrules. We have an example of a no chondrule sign over here at the left, and as a differentiated stony meteorite here at the bottom right. Differentiated meteorites come in three basic varieties. The stones, which are mainly basalts, they're from the crusts of melted and differentiated bodies. There's the irons that consist mainly of metallic iron-nickel alloys. Most have a Widmanstätten structure due to subsolidus cooling. And most of these iron meteorites are pieces of the cores of differentiated asteroids. Finally, and to the main topic of today, we have the stony irons. These are mixtures of metallic iron, nickel, and silicate rocks. There are two main groups of stony irons, which we will discuss today, the Pallasites and the mesosiderites. When we differentiate a planetesimal or an asteroid like this, we may get sort of pods of liquid, as we see here on the left. As the asteroid continues to melt, the metallic liquid will sink to the gravitational center of the body to form a core. The silicate liquid will crystallize into the crust and mantle. The first type of differentiated meteorites are the stones. They have igneous textures formed by crystallization from a magma. The salts formed in the crust, diogenites, another form of differentiated stony meteorite, they form in the upper mantle. The picture here is of the Milbilili eucrite from Australia. We have the iron-nickel phase diagram here. At the very top, L stands for liquid. At these very high temperatures, all the metal is a liquid. As the liquid cools, it begins to crystallize, and we get this gamma phase, that's taenite, at high temperatures. When we reach the solvus down there at the bottom, sort of right over here, the metal, the taenite, will start forming a low nickel phase at its expense, the alpha phase, which is camosite. And so camosite and taenite will crystallize together as both become richer in nickel, as more and more of the low nickel phase camosite precipitates from the original taenite crystal. We will get a Widmanstätten structure, as we see here. This is the subsolidus intergrowth of the two iron-nickel phases, the low nickel phase camosite and the high nickel phase taenite. The camosite grains occur parallel to the four sets of octahedral planes within the parent taenite crystal. And if we cut the octahedron here at different faces, we will get different Widmanstätten patterns. Here's a picture of the Henbury 3AB iron meteorite. Iron meteorites constitute discrete groups discrete chemical groups. Each is derived from a separate asteroid. The groups can be distinguished from one another by their bulk chemical compositions. If we look at the diagram here, which is cobalt versus gold, we see that these different groups, which are characterized by a Roman numeral and a 1 or 2 letter suffix like 2F or 3AB, we can see that these form linear arrays on a diagram such as this. And most of these arrays are due to fractional crystallization in the metallic core. If we have a body such as Vesta, which is the second largest asteroid and a differentiated body, we have a cross section of it. It will look something like this. We will have eucrites in the crust. These are basalts. We will have diogenites, which are orthopyroxene-rich igneous meteorites. These will be from the upper mantle. Howardites are the mechanical mixtures of eucrite material and diogenite material. These three groups, the Howardites, the eucrites, and the diogenites, are the HEDs. We may have iron meteorite, well, an iron core, and 3AB-like iron meteorites will be materials that constitute a core like the one in Vesta. And at the core mantle boundary, we will get pieces of the upper core, the metal, and pieces of the lower mantle, the olivine-rich material, and we will form Pallasites, which are thought to be derived from the core mantle boundary of a differentiated body like Vesta. Parent body collisional disruption is the means by which magmatic iron meteoroids and Pallasites are flung into interplanetary space. We have a differentiated body over here. Irons are in the middle. Pallasites are at the core mantle boundary here. A large projectile comes in, shatters this body, and these different chunks of the body, the stony material, the Pallasite material, and the iron material, are launched into interplanetary space. Pallasites, as I said before, are samples from the core mantle boundaries of differentiated asteroids. So we have a diagram over here. On the left, we'll have the metal sinks to the center, and we have a molten iron nickel material here. We have an olivine-rich mantle as it begins to crystallize, and when it eventually solidifies and then suffers subsequent impacts, we will have a solid iron nickel core and Pallasite material there at the core mantle boundary, the mixture of the lower mantle and upper core. Pallasites, as we see here, are these olivine metal mixtures. Olivine are these green, yellow, brownish silicate material here, and the metal is this white or light gray material. And so the Pallasites are these mixtures. Pallasites can be divided into several categories. There's the main group Pallasites, abbreviated PMG, which constitute about 82% of all known Pallasites. There's the Eagle Station Pallasites, abbreviated PES for Pallasite Eagle Station. These are about 7% of the known Pallasites. And there's ungrouped Pallasites, which are the remaining 11%. A few of the ungrouped Pallasites are particularly noteworthy, such as Vermilion and Yamato 8451. These particular Pallasites are commonly called pyroxene Pallasites because, again, they are rich in pyroxene. Here's an example of a main group Pallasite, a PMG. This is Imilak. Here's Krasnoyarsk. This is the first Pallasite to be discovered and described, first one to be recognized. It's very weathered. It was discovered in Siberia in 1749. Its total known weight is about 700 kilograms. And it was investigated by Peter Simon Pallas in 1772, who looked at this rock, which he assumed was an iron, and then he had it transported eventually to St. Petersburg via Krasnoyarsk. The main group Pallasites, the PMGs, I will talk about right now. Although Pallasites are often said to be half metal and half olivine, the actual modal abundance of olivine in different main group Pallasite specimens varies from about 35 volume percent to 85 volume percent, but the average is roughly 50%. Olivine grains occur as individual crystals or crystal fragments ranging from about 1 millimeter in size to about 3 centimeters in size. And they also occur as constituents of sub-rounded to sub-angular polycrystalline aggregates that can be up to 30 centimeters in maximum dimension. Here's a picture of Fukang. This is a very large Pallasite. We can see the metal, which is the white stuff around it. The olivine grains occur as individual grains, individual grain fragments, and as aggregates, masses, which can be fairly large. The large olivine aggregates are moderately intact chunks derived from the asteroid's lower mantle. Here's a piece of Simchan, and we can see here that there's large olivine-free metal-rich areas, and then also chunks that are very rich in olivine, although some metal is indurated within it. A few of the main group pallasites and the anomalous main group pallasites contain large olivine-free regions that are up to 7 centimeters in Esquel, up to 20 centimeters in Brenham, and up to 30 to 40 centimeters in Simchan. These large metal regions commonly display Widmanstätten patterns, and they're essentially olivine-free. Here's a piece of Simchan, which we can see has very little olivine in the middle of it, essentially none, and some olivine is over in the upper left and lower right. If we fashion a couple of spheres from Simchan, the one on the right might be fairly typical with the olivine metal mixture, but the one on the left is also Simchan, which is olivine free, and this looks like that of an iron meteorite. Here's Brenham showing very large olivine free regions within it. The majority of pallasites have angular olivine grains, such as Esquel, Simchan, Admire, Huckata, and Imelak. A minority have rounded olivine grains, such as Springwater, Thiel Mountains, Brenham, and Krasnoyarsk. If we look at Esquel, we can see a typical pallasite there with angular olivine grains, shards, and fragments. If we look at Springwater, we see that the olivine grains are rounded. Here's a larger picture of Springwater, and you can see that there are many, many olivine grains, and they're essentially all rounded. The rounded olivine grains probably developed from angular grains during annealing. Here's a diagram from Ed Scott from 1977. So the idea would be that all the pallasites started off with angular grains, such as picture number 1 here at the top right, and then from an annealing process, as surface energy is diminished, the grains begin to get rounded, and we can see that the situation is depicted here. Here's Brenham. Here's the main mass of Brenham, a 635 kilogram body, proudly displayed by Steve Arnold. Brenham is also featured on this $5 coin from the Cook Islands with Queen Elizabeth's visage on it. We can see over here on the obverse of the coin an actual piece of Brenham here in the ground, a fireball, the moon, some stars. The Eagle Station pallasites, the abbreviated PES, there are currently 5 members of this group. The traditional ones are Cold Bay, Eagle Station, and Itzawissis. 2 more have come in since then, whose names I will mangle if I pronounce, so I will just leave them here on the screen. These Eagle Station pallasites have textures like those of the main group pallasites in that they consist mainly of olivine enclosed in metallic iron nickel. Olivine grains in these guys are angular, they tend to be fractured, and less than 1 centimeter in size. If we look at a diagram of chromium isotopes versus oxygen isotopes, we can see that solar system materials are divided into 2 different groups. This was shown by Paul Warren a few years back. And the Eagle Station pallasites over there at the upper left fall amongst the carbonaceous-chondrites. And so these are carbonaceous materials. Most of the rest of the solar system are non-carbonaceous. This includes the Earth, the Moon, Mars, the HEDs, the mesosiderites, and the main group pallasites. They're very distinct. They're from different regions of the solar system and obviously from different parent bodies. In the typical oxygen isotope diagram, we can see that the main group pallasites are there just below the terrestrial fractionation line in blue, abbreviated PMG, and the Eagle Station pallasites, PES, are very close to the carbonaceous-chondrite anhydrous minerals line, showing that they're related to carbonaceous chondrites and not to the non-carbonaceous materials like the ordinary, like the main group pallasites are. The Eagle Station pallasite minerals are more oxidized than the corresponding phases in the main group pallasites. For example, the Eagle Station pallasite olivine have much higher FeO contents. They average about phthalate 20, whereas those in the main group pallasites average about phthalate 12 or so. They also have different iron to manganese ratios. The Eagle Station pallasites iron manganese ratio is 104. The ratio in the main group pallasites ranges from about 35 to 60, much different. Here's a couple pictures of Eagle Station, Cold Bay, Itzawissis. There are about 12 times more main group pallasites than Eagle Station pallasites. The small proportion of Eagle Station pallasite members is probably in part, perhaps a large part, a function of the relatively high oxidation state of their parent body. In other words, if a lot of the iron is oxidized as FeO, it'll appear in silicate and not be in the reduced form in metal. So after melting and differentiation, this oxidized asteroid would likely have had a small iron core encircled by a narrow spherical shell of mixed olivine metal material, i.e. pallasite material. If we look at a schematic diagram of what the main group pallasites, the PMG pallasites may look like, and the Eagle Station pallasites, the PES asteroid would look like, assuming they were the same size, and we do not know that to be true, it would look something like this. The main group pallasites would have a large metal core, a fairly thick core-mantle boundary, because a lot of the iron would not be in the oxidized state, it would be in a reduced state to give you a larger metal core. But in the Eagle Station parent asteroid, more of the iron is oxidized, so the silicate proportion of the asteroid would be higher, the metal core would be smaller, and there would be a smaller spherical shell of the core-mantle boundary, so there'd be less pyroxene, there'd be less of the Eagle Station pallasite material, which accounts in part perhaps for the fact that there are far fewer Eagle Station pallasites than main group pallasites. Now to the pyroxene pallasites. This is an ill-defined grouplet, the pyroxene pallasite grouplet. It consisted initially only of vermilion and Yamato 8451. Vermilion contains about 5 volume percent pyroxene, but in contrast, main group pallasites contain far less than 1 volume percent pyroxene. Vermilion and Yamato 8451 have nearly identical oxygen isotopic compositions, which are distinct from those in the main group pallasites and the Eagle Station pallasites. They're clearly from a different body altogether. Here is vermilion, one of the pyroxene pallasites, and we can see here on an oxygen diagram, the pyroxene pallasites, the red triangles there, have a far different oxygen isotopic compositions than the blue circles indicating the compositions of the main group pallasites, which we can see are very similar to the HED samples. Okay, on to mesosiderites. Mesosiderites are an enigmatic group of stony iron breccias, averaging roughly 50 weight percent metallic iron nickel, troilite, and tribracite, but the actual range of metal is about 18 to 90%. The troilite ranges from about 0.6 weight percent to 14 weight percent, and there's only a little tribracite altogether. Also, they roughly 50 weight percent silicate are in these mesosiderites, but the actual range of silicate goes from 28 to 80 weight percent. The silicate phases include orthopyroxene and plagioclase and minor calcium pyroxene, olivine, and tridymite. Also present are minor to trace amounts of marylite, chromite, and ilmenite. There are 3 compositional classes of mesosiderites. There's the class A mesosiderites, which are relatively rich in plagioclase and calcium pyroxene. Samples contain about 55 volume percent orthopyroxene, 29 volume percent plagioclase, and 6 volume percent tridymite. There's the class B mesosiderites. They're more ultramafic and they're relatively rich in orthopyroxene. So they contain about 76% by volume on average of orthopyroxene, which is much more than those of class A. They contain 17 volume percent plagioclase, much less than the class A, and about 2% tridymite, again, about 3 times less than those of the class A. Class C mesosiderites are represented by only one sample, Reckling Peak 79015, which has very abundant orthopyroxene. One silicate-rich region contains 67 volume percent orthopyroxene, but only 0.2 volume percent silica and no plagioclase or olivine at all. There are 4 textural subgroups of mesositerites. The type 1 samples are the ones that have not been recrystallized. These are fine-grained, unrecrystallized rocks. They have a cataclastic texture and contain distinguishable grains as small as a few microns in size. There are angular grains and grade fragments, which are easily discernible. Type 2 samples are more recrystallized, although they still have a recognizable cataclastic texture. The matrix is coarser grained, mostly more than 10 microns in size, and only the larger class are angular. The smaller class have been texturally integrated during heating, annealing, metamorphism into the matrix. The type 3 samples are very recrystallized. They have plagioclase poikilolytic textures. They have large plagioclase grains, several millimeters in size. These enclose about 100 micron size, rounded to euhedral grains of orthopyroxene. The type 4 samples were partly melted and have been described as melt matrix breccias. They have intergranular textures consisting of orthopyroxene surrounded by plagioclase laths. It's very likely that going from type 1 to type 2 to type 3 to type 4, there's an increase in the amount of heating there, probably due to impacts. Here is a mesosiderite. This is Hainholz, a type A4. Again, the compositional class is A, indicating a certain amount of orthopyroxene and plagioclase in it. And type 4, meaning it's been subjected to impact heating. And so the large metal nodule there that you can see near the middle is due to some of the metal melting and then glomming together. Here's Crab Orchard. This is an A1 mesosiderite, indicating, again, the compositional class is A, and type 1, meaning it's unrecrystallized, unmetamorphosed, and has experienced not appreciable amounts of impact melting. Here's NWA 8402, a type A3 mesosiderite. If we look at the oxygen isotopic diagram here, we can see that the eucrites here are the open circles. The mesositerites are the red triangles, which we can see just fall among the HED samples. The main group Pallasites are the open squares, and the IIIAB irons are the open triangles. And we can see that all these things form along a fractionation line, indicating that they all have the same oxygen isotopic compositions. Silicate in mesositerites occurs admixed with metal and troilite as fine grains. It also occurs as clasts and pebbles, ranging in size from about a millimeter or so, probably somewhat less than a millimeter, to 12 centimeters in size. Most of the clasts are basaltic, gabbroic, orthopyroxenitic, or impact melts. Also present in some mesositerites are rare donitic and anorthositic clasts. I'll be discussing more about these things shortly. Here's a picture of a mesosiderite, NWA 2932. It has some large metal nodules in it. And then outside the metal nodules, we can see that there's some segregation of the metal and the silicate. Here's Reckling Peak 79015, the only representative of the class C mesositerites. It's sometimes called anomalous. Certainly has a peculiar texture, probably due to impact melting. Here's Vaca Muerta, a type A1 mesosiderite. This, again, the 1 indicates that it has suffered very little impact melting. It has a cataclastic texture. And the metal and silicate are well mixed together. There are some clasts in here, as we can see. Here's a small piece of Vaca Muerta. Here's Esterville. This is, again, type A, as is Vaca Muerta, as we see here. But it is its textural type is 3/4, indicating it has suffered appreciable amounts of impact melting. If we look at this picture of Esterville, both in reflected light on the left and transmitted light on the right, we can see there's large accumulations of metal, the white stuff, which has been melted, glommed together, and has surrounded some silicate fragments. The silicate actually also has a ragged boundary, indicating it's been somewhat melted. There's not a lot of small metal grains in the matrix because the metal has sort of pooled together. Again, probably due to impact melting processes. Here's another piece of Esterville. We can see a large metal nodule which is formed, and there's not a lot of metal we can see at the left because the metal has formed these large nodules. Here's Chinguetti, a type B1 mesosiderite. Here's Mincy, a type B4, and Bondoc, another B4. Bondoc, as you can see, has some large metal nodules in it. Mincy has one at the bottom right. The large clasts in mesositerites can be divided into 8 types. There's the polygenic and monogenic cumulates, which constitute the largest group of these class, about 39% of the class. These are coarse-grained gabbros that are highly depleted in incompatible elements. One Vaca Muerta pebble has an H-chondrite normalized europium-samarium ratio of 251, the largest such fractionation known among solar system rocks. I'll explain more about that shortly. The second largest class category are these polygenic basalts. These are finer grain rocks. They constitute about 30% of all of the large class. Next come the quench textured rocks resembling impact melted eucrites. These are impact melts that cooled very quickly. Next come the quench textured rocks resembling impact melted cumulate eucrites. There are monogenic basalts resembling basaltic eucrites. They're hardly distinguishable from independent eucrite meteorites. There's also ultramafic cumulate rocks consisting of large crystals of orthopyroxene. These resemble diogenites. There's ultramafic cumulate rocks consisting of large crystals of olivine. These are essentially dunites. And in Mount Padbury mesosiderites, some of these olivine crystals are up to 10 centimeters in size. And the least abundant of these class are anorthositic class that are several millimeters across. Here's a pebble in Vaca Muerta. You can see at the bottom over here is the normal mesosiderite matrix with intermixed metal and silicate. Then we have a large pebble here, a silicate pebble here with essentially no metal in it at all. Okay, I want to talk a little bit about compatible elements and incompatible elements during the crystallization. Here we have a schematic diagram of an olivine crystal and surrounded by a magmatic liquid. Compatible elements are those elements that tend to enter the solid, tend to enter the crystal during crystallization. The incompatible elements are not compatible with the crystal, hence the name, and they tend to remain in the liquid. When olivine crystallizes, magnesium tends to enter the crystal, whereas iron, silicon, calcium, and aluminum tend to remain in the melt. So as the liquid crystallizes, we will get 4-85, for example, in this case here, which is a lot of magnesium that crystallizes first, and then the iron concentration increases in the liquid. So the next olivine layer to form is forming from a more iron-rich liquid. So the phosphorate content goes down from 85 to 80 in this case, and then later to 675 and so forth, and then 68. The fact that it goes up again over here indicates that there was probably another magmatic liquid that came in this particular instance. Let's look about rare earth elements. Rare earth elements are incompatible. They do not easily enter the crystal. The incompatible elements remain in the melt, these including the REEs, the rare earth elements. And so the cumulate material, like here at the bottom, is very low in incompatible elements. The incompatible elements remain in the liquid. These materials sink to the center. And so the material here in this cumulate layer will be very low in incompatible elements, very low in rare earths. The exception is europium. The rare earths are generally trivalent and remain in the liquid, but europium is divalent, has a +2 valence. It substitutes for calcium and plagioclase. It's therefore compatible and goes into the plagioclase crystals, is not depleted in the cumulate material if the cumulate material contains plagioclase. So if we look at the rare earth element abundances in Vaca Muerta silicate pebbles in this paper here, by Rubin and Jurdy, we can see that some of the pebbles are eucrite-like. Those at the top have relatively flat rare earth element patterns, as do the eucrites. One of the pebbles from Vaca Muerta is cumulate eucrite-like. It is not as flat. It's somewhat depleted in light rare earth elements, such as lanthanum, cerium, and neodymium, and samarium. It has a fairly high positive europium anomaly, so it has a high europium samarium ratio. But we discovered some of these enormously rare earth element depleted clasts. They're extremely low in rare earth elements. In fact, we couldn't even measure the lanthanum, samarium, and neodymium in them. They have very low samarium contents because they, again, are like supercumulate eucrites. They've been, incompatible elements have been squeezed out to an enormous extent. Perhaps there was an impact melt, we had a form of cumulate eucrite, and that itself was impact melted, and then formed another cumulate from that. So the rare earth element contents are very low. However, because europium is not incompatible, it remained there in the plagioclase crystals. And so we have extremely high europium to samarium ratios, the highest known among solar system rocks. Here's a large diagenitic clast in the emery mesosiderite. This is very rich in orthopyroxene. Here's Mount Padbury, a type A1 mesosiderite. Here's a large olivine clast. Mount Padbury contained olivine clasts up to 10 centimeters in size. In 1981, Frank Kite at UCLA discovered small fragments of an anomalous metal-poor mesosiderite named L-tannin. This occurred within late Pliocene deep-sea drill cores in the Bellingshausen Sea on the west side of the Antarctic Peninsula. These deep-sea drill cores are from sample and age about 2.15 million years before present. He found about 1.7 grams of intact mesosiderite fragments there, but in addition to those mesosiderite fragments, there were particles of a vesicular impact melt. Frank Kite estimated that the L-tannin projectile contains only about 4 weight percent metallic iron nickel. Here's a picture of L-tannin over here, the 500 micron scale bar. Further work showed that the impact debris occurred in at least 3 different L-tannin cores that were from sites separated by more than 500 kilometers, indicating that a large dispersal of this material, suggesting that the projectile was large, perhaps 1 to 2 kilometers in diameter. Okay, some years ago, in 1990, Hassanzadeh et al., again, UCLA work, analyzed a bunch of different metal nodules in different mesosiderites and found that almost all of them, or all of them, were very similar to H-chondrite metal and the bulk 3AB core. The metal nodules are so similar to one another, it suggests that they were not from a fractionally crystallized core, they were from a core that was largely molten. The metal had not undergone significant fractional crystallization and hence was still largely a liquid. So we can make some constraints on mesosiderite origin. The mesosiderites have little olivine, indicating that much of the mantle material is missing from its parent asteroid. Metal in most mesosiderites is interconnected in 3 dimensions and exhibits a limited compositional range, indicating that the metal was molten or very largely molten when it was mixed with the basalt. Metal has chondritic siderophile element ratios, indicating that it had not undergone extensive fractional crystallization in a cooling core before it mixed with basalt, again, consistent with it being largely a liquid. In 1983, Roger Ewan summarized different mesosiderite models, most of which are bad. The first one I'll discuss is the foundering and sinking of a basaltic crust through a molten mantle and settling of the crust atop the core. We can see the advantage of this model. We get basalt from the crust. We have the liquid iron core there at the bottom, so we can founder and sink the basaltic crust to the iron core. We can get the 2 of them mixed together. We just have to get rid of the olivine by some sort of subsequent impact. A problem is that the liquid mantle will have a melting temperature appreciably higher than that of the basaltic crust sinking, and so it would tend to melt these blocks of sinking basalts. So that is a difficulty with it. Powell in 1971, Ben Powell, suggested that there may have been near-surface segregation of metal and silicate melts, followed by subsequent extensive brachiation and deep burial, generating mesosiderites. The problem is that why didn't the metal sink to the to a core if there was melting, and why there's so little olivine. Another model might be here. That this is also from Ewan's. Some impact models related to mesosiderites, as he had here on the left. We have cratering. He said could not excavate core metal without destroying the body, so any metal in the ejecta must come from projectiles. In the center, there's a disruption and reassembly after collision of 2 bodies to produce stony-iron meteorites, but again, where is the missing olivine material? And then on the right diagram is cratering after a violent collision, but the asteroid would probably be destroyed. Again, why is there so little olivine? That is a problem in all of these things. Jerry Delaney in 1983 suggested 2 different models for mesosiderites. On the left side, we have during core formation metallic liquid was from the core was turbulently mixed with crustal material, somehow leaving out the olivine mantle. Doesn't seem likely. And right prior to core formation, we had a giant basin we excavate to a certain depth, forming stony iron breccias. Again, the problem is, why is there so little olivine from the mantle? All these models involve a single parent body. They all have difficulty accounting for the paucity of olivine from the mantle. Watson and Rubin in 1985 proposed that mesosiderites were formed by the collision of a largely naked metal core projectile with a basaltic crust of a much larger asteroid. This avoids the missing olivine problem because we don't penetrate the olivine in the olivine mantle in the target asteroid. Refined models indicate that the metal projectile was largely molten, which leads to this refined model, which is the one I prefer for the likely origin of mesosiderites. Over here, we have a relatively small projectile. Actually, it's fairly large, but it's largely molten metallic iron nickel projectile early in solar system history before the metal core was able to crystallize appreciably. And this is the dislodged core of a disrupted differentiated asteroid. And it just impacts the basaltic crust of this differentiated asteroid, which has a solidified basaltic crust over here. At the time, it had a partly molten olivine-rich mantle and a largely molten iron-nickel core. So again, early in solar system history, before there had been appreciable crystallization of the cores, one of these asteroids got destroyed, and the core fragments impacted at some only moderate velocity the basaltic crust that had already formed in this differentiating asteroid. Okay, that is all I have for you today. And so thank you for watching. Thank you so much.